if we take the weight and replace it by two equivalent vectors, a vector in this direction and a vector, or two equivalent forces, a force acting down the plane and a force acting in the opposite direction of the normal force. That is, a force that's perpendicular to the incline. So we have a force perpendicular and a force parallel to the incline. It certainly is possible to have two such forces that have exactly the same effect as the weight. Pulling this way and this way with just the right forces could give us the same effect as this weight. If we replace the weight by these two forces, we see the condition for the equilibrium situation that we saw. Equilibrium means net force zero. When the rail moved down the incline at a constant speed, a constant velocity, it was in equilibrium. It was experiencing zero net force because it was not accelerating. Its acceleration was zero. So we replace the weight by these two forces, and we see that if this weight is just exactly equal to the frictional force, and if the normal force is exactly equal to this force, which we call the perpendicular force of the weight, the component of the weight that's perpendicular to the incline as opposed to the component that's parallel to the incline. Okay? If this force is exactly equal to the normal force required to support the rail, then we do have equilibrium. And this is exactly what happens when the ramp slope reaches the point where this parallel component is identical to the frictional force. As the ramp slope increases, this component of the force increases. If the ramp is flat, the weight and the normal force balance each other out. We don't need a force along the ramp, and there's no friction. But we do reach a point where the force here reaches the maximum possible frictional force between the rail and the ramp, and then we have what's called an equilibrium situation. And we'll deal more with that after we learn to manipulate vectors. But here's the idea.